The continuous demand for enhanced cellular networks has driven crucial improvements in network assessment methods. Traditional drive and walk tests, however, face challenges such as limited altitude assessment and difficulty in accessing hard-to-reach areas. To address these limitations, this project aimed to develop a drone-assisted cellular coverage monitoring system that integrates real-time LTE parameter visualization via a dashboard and a machine learning application to predict LTE coverage at high altitude using ground-level data. This system integrates software and hardware. The software, developed entirely in Python 3.13, includes PyQt5 for the user interface, PyQt Graph for dashboard visualizations, and Folium for interactive heat maps. For predictive feature, the system utilizes machine learning algorithms such as XGBoost, LightGBM, SVR, gradient boosting regressor, and random forest regressor. On the hardware side, the core of the drone is the Cube Pilot Cube Orange Plus flight controller, with power managed by an LM2596 DC to DC buck converter that steps down 25 volts to 20 volts. The system's connectivity is illustrated by a 25-volt lithium-ion battery powering the step-down module to provide 20 volts to a MikroTik LTAP LTE6 kit, which acts as a client, which then wirelessly communicates with a laptop, which is the server of the system. The project uses a device called MikroTik LTAP LTE6 kit, which is a compact LTE-capable wireless access point. It was used for both drive tests and drone-based testing as equipment for collecting data on cellular network parameters. The device comes with a powerful built-in operating system called RouterOS. This combination provides a reliable platform for data collection. To collect network data from the device, a server, which is a laptop or a single-board computer, runs a local Flask web server, which, after connecting to the MikroTik's access point, receives collected network data through an HTTP post request to its upload endpoint. This received data is then logged into a file and stored in a CSV file, making it available for further processing and analysis. In the case of the machine learning model, random forest algorithm was chosen due to its outstanding performance. That said, the selected features were altitude, distance to primary and secondary base stations, and ground-level LTE parameters, while the label of the model was RSRP at high altitude. The dashboard and trained machine learning model are integrated into a single software user interface, LTE Vision, which was developed using Python. This is the first page of the dashboard, which displays plots of common LTE parameters such as RSRP, RSRQ, and RSSI. Additionally, there are gauge charts illustrating the current network strength and the average network strength for the past few minutes. The page also includes other information regarding the LTE network, such as the telecommunication provider and details about the current cell tower being used. This is the second page of the dashboard, which is a real-time map displaying a heat map. This heat map visually represents the LTE signal strength, specifically RSRP, across a geographical area, depending on the current location of the user. Different colors on the map indicate varying levels of RSRP, allowing the user to easily identify areas with excellent, good, mid-cell or cell edge. Since the dashboard updates data at approximately 1-second intervals, this heat map provides a dynamic and quick overview of the LTE signal strength as it changes in real time. This makes the dashboard an efficient tool for monitoring LTE network coverage, especially during drive tests due to its real-time capabilities. The software user interface can also generate heat maps from collected data for post-analysis purposes. In this case, the input file must be in CSV format and include latitude, longitude, and RSRP values. This feature allows users to visually identify areas of varying signal strength across a geographical region. This can be helpful for in-depth historical trend analysis and long-term network planning, complementing the software's real-time heat map capabilities, which offer immediate insights into current network conditions. Finally, let's discuss the integration of the machine learning model within the user interface software. On the prediction page, two buttons are available. One to load the dataset and another to initiate prediction on the loaded data. To begin prediction, the dataset must be in CSV format and contain all the necessary parameters. These parameters should include all features used by the random forest model, as previously mentioned, along with latitude and longitude. The prediction results are then displayed in a table, showing the longitudes, latitudes, the model's features, and the corresponding predicted outcomes. The predicted RSRP at the desired high altitude is presented in the far right column of the table, adjacent to the ground level RSRP, for ease of comparison. In conclusion, this project offers a versatile approach to cellular network assessment. By utilizing drones to evaluate networks in challenging terrains, it significantly reduces reliance on expensive ground-based equipment and extensive manpower, leading to faster data collection and more detailed information for accurate assessments. Furthermore, the integration of machine learning models allows for the prediction of high-altitude network quality from ground-level data, which is particularly beneficial for hard-to-reach areas. This capability enhances optimized network planning at higher altitudes. Ultimately, the project's innovative methods also contribute to environmental benefits through reduced fuel consumption and emissions compared to traditional drive testing.